In this video, we discuss the form of the solution of a linear, non-homogeneous ordinary differential equation. And we also discuss the superposition principle for homogeneous linear ODEs and the superposition principle for non-homogeneous linear ODEs. So here is a non-homogeneous linear ODE, and let's say that's nth order. So you've got that coefficient function times the nth derivative, plus a coefficient function times the next lower derivative, plus another coefficient function times the next lower derivative, and so on, until eventually you have a coefficient function times the first derivative, plus a coefficient function times your dependent variable, and that's going to equal some function on the right-hand side. Now, if a differential equation can be written like this, and this function on the right-hand side is not equal to the zero function, that's what makes this a non-homogeneous ordinary differential equation. The fact that y and y's derivatives either appear to the first power or they don't appear in the equation at all if the coefficient function happens to be zero. And if all of those coefficient functions are also depend only on the independent variable at most, and the function on the right-hand side after rearrangement depends on the independent variable at most, that's what makes it linear. It's nth order because the highest order derivative is the nth derivative, and it's an ODE because these are ordinary derivatives. This is an nth order linear non-homogeneous ODE. Now, if we want the general solution to this, we do this. And I'm going to come back to this in just a moment, this other piece. My handwriting went up when I was writing about that. I remember reading somewhere a long time ago about handwriting analysis. I must have gotten excited when I was talking about the superposition principle for non-homogeneous linear ODEs. So we'll go back to that in just a second. So here is the general solution of a non-homogeneous linear ODE. This is the form of the general solution. It has two pieces. The first piece is called y sub c, and the second piece is called y sub p. And this is where y sub c is the solution, or the general solution, of the corresponding homogeneous differential equation. Now, y sub c has some names. It's called the complementary solution. It's not giving you complements, it's complementing the particular solution. It's an E, not an I. Or sometimes it's called the complementary function. And y sub p is a particular solution to the non-homogeneous ordinary differential equation. Now, when I first learned this as a student, I thought, why on earth do we have to have two parts? If that's a solution to the differential equation and we have a solution to the differential equation, why do I have to add this? And the reason is because we're trying to find a general solution. This is the one solution that contains all possible solutions to the non-homogeneous equation. So this is not enough. If I want the solution family that contains them all, I need this as well. Now remember, the solution to the homogeneous differential equation, that's where the right-hand side is zero, let's see, the general solution of an, well, actually no, of a homogeneous linear ODE has this form. And we still haven't talked about how to find these pieces. We're going to talk about how to find these pieces in the rest of the chapter, the rest of this unit. But the general solution has this form for the homogeneous differential equation. So if it's an nth order equation, Oh, that's what I was thinking of an nth order homogeneous linear ODE. It looks like this. It has n linearly independent solutions. You multiply them by constants, you add them together. That's the general solution. So if it's a third order differential equation, you're going to have 3 linearly independent solutions. You multiply them by constants and add them together. And that's the general solution of the homogeneous ODE. So what this is telling us is that if you have a non-homogeneous ODE, first you solve the corresponding homogeneous ODE. And you find y sub c, the general solution of that corresponding homogeneous ODE. So if it was an nth order equation, y sub c is going to have this form. You'll find the n linearly independent solutions. You'll multiply them by constants and add them together. That will be your y sub c. And then you're going to need another method to find y sub p. We're going to learn a couple of methods in this class. Once you find y sub p and you've found y sub c, you're going to add those two together, and that's the general solution of the non-homogeneous equation. To make this more concrete, we'll look at an example in just a moment. But before we do that, I want to talk about the superposition principle for homogeneous linear ordinary differential equations. So here it is. We already stated it. We just didn't call it the superposition principle. It just says that if y1 and y2 are solutions of a homogeneous linear ODE, then y equals c1y1 plus c2y2 is also a solution. So that superposition comes from multiplying those two functions by constants and adding them together. So we're thinking of that as a superposition of two functions. I don't know why I just didn't leave very much space there. This is looking pretty messy. Sorry about that. Now, the second superposition principle comes for non-homogeneous equations. Now, here's the idea. Let's say you've got a linear differential or a differential equation that looks like this, and this left-hand side is exactly the same for both of these differential equations. This left-hand side is sometimes notated this way. Since this is a linear differential equation, this is sometimes called L applied to y. That's a linear operator. This L operator takes y and it multiplies it by this function, and then it takes the nth derivative and it multiplies by, and then it adds this function times the n minus 1th derivative, and it adds the next coefficient function times the n minus 2th derivative, n minus 2nd derivative, I guess, and so on, and you go all the way down the list. That's what that L means. So let's say that this left-hand side is just represented by Ly. So, and you've got two different differential equations. So let's say we've got L applied to y equals g sub 1 of x. If this differential equation has the solution y sub p sub 1, that's our particular solution. And this other differential equation, L applied to y equals g sub 2 of x, has this solution, y sub p sub 2. Then if I'm looking at this new differential equation, L of y equals a constant times g1 plus a constant times g2, then, or if this has this solution and this has this solution, then this, has this solution. Y sub p equals c1 times y sub p sub 1 plus c2 times y sub p sub 2. And I know that that's pretty abstract, but what this is saying is if the left-hand side of the differential equation is exactly the same, and when you have this right-hand side, you've got this particular solution. And when you have this right-hand side, you've got this particular solution. If we take those right-hand sides and we multiply them by constants and add them together, if we know the solution to this differential equation and this differential equation, to find the solution of this differential equation, we just multiply by the same constants and we add them together. And that's going to give us a solution to this new differential equation. That's called the superposition principle because we're taking two solutions and we're multiplying by constants and adding them together, which is a superposition of those two functions. Okay, so let's look at some concrete examples. So here we've got a non-homogeneous differential equation. We can tell that it's non-homogeneous because of the form of the right-hand side. This is our g of x. It's not equal to 0. And this has a solution, y sub p sub 1 equals this. Now, if you're asking yourself, how do they find that? We're going to learn how they find that later in the semester. It's a method called the method of undetermined coefficients. You can also use a method called variation of parameters, but in this case, it would be better to use the method of undetermined coefficients. So y sub p sub 1 will be found using that method, and we get this answer. And I'll call this g of 1, g sub 1 of x. So suppose that this differential equation has this solution, and this differential equation, where this is g sub 2 of x, has this solution. So what this is telling us before we move on is that if I take the first and second derivative of this and I plug this into the left-hand side, I'm going to get 6x squared after I simplify. Or if I take the first and second derivative of this function and I substitute that into the left-hand side and simplify, I'll get this function. This question says, then is it possible to use those to find the solution of this? Well, I think it is possible because this 3x squared plus 1 is actually just 1/2 of g sub 1 of x. And this 24 times e to the 3x is actually just -2 times that function. So we can use the superposition approach here. And here it is. We'll say, yes, it's possible. Y double prime minus 6y prime plus 9y equals 3x squared plus 1 plus 24 e to the 3x is the same as 1/2 times 6x squared plus 2 minus 2 times -2 or -12 e to the 3x. And that's 1/2 of g sub 1 of x minus 2 times g sub 2 of x. According to the superposition principle, that means y sub p is equal to 1/2 times y sub p sub 1. That is a particular solution corresponding to the differential equation given by this equals g sub 1, minus 2 times y sub p sub 2, where y sub p sub 2 is the particular solution corresponding to y double prime minus 6y prime plus 9y equals g sub 2. The superposition approach tells us that if this is just a multiple of g1, y sub p would just be that 1/2 times this. And if this piece is just a multiple of g2, y sub p for that piece would just be -2 times g2. And then if I want the solution for this combination, where both of these are added or subtracted on the right-hand side, well, I just take 1/2 of the solution that goes with that g1, and I subtract 2 times the solution that goes with g2. So if I substitute those in, this is what I get. I've got 1/2 of 2/3 x squared plus 8 over 9x plus 2/3. And then here I've got -6x squared e to the 3x And if we simplify, we get 1/3 x squared plus 4/9 times x plus 1/3. And then if we distribute that -2, we get plus 12x squared times e to the 3x. This is the solution of this differential equation by the superposition principle. Now, I'm not going to prove that superposition principle, but we could easily prove it using what we talked about before. If this is my new differential equation, and y sub p sub 1 is a solution of this, and y sub p sub 2 is a solution of this equation, if you substitute this into the left-hand side over here, and then you regroup everything, through grouping, you'll be able to show that this linear operator applied to this y sub p will give you c sub 1 times a linear operator applied to y sub p sub 1, which would give you g sub 1, plus c sub 2 plus the linear operator applied to y sub p sub 2, which would give you g sub 2. So this can be proven in the same way that we proved this superposition function or superposition principle for homogeneous linear ODEs in the other video. Okay, that's the idea. Now, I'm not going to prove it in this video, but if you want me to, just let me know and I can make another video where I prove that. Now, if you're thinking to yourself, okay, but that's not the general solution of this differential equation, you're absolutely right. In order to find the general solution of, let's just look at that top differential equation. Let's say you're asked to find the general solution of y double prime minus 6y prime plus 9y equals 6x squared plus 2, given that y sub p equals 2/3 x squared plus 8/9 times x plus 2/3 is a solution. And y sub c equals c1 e to the 3x plus c2 times x e to the 3x is a solution not of this differential equation, but of this differential equation, y double prime minus 6y prime plus 9y equals 0. Well, according to the definition of the general solution of a non-homogeneous linear ODE, the general solution is y sub c plus y sub p, where y sub c is a solution of the corresponding homogeneous equation. The corresponding homogeneous equation is right here. Now, when we learn the method for solving homogeneous linear ordinary differential equations with constant coefficients, we'll be able to prove that this is the solution to this equation. So the general solution includes y sub c, which is this, c1 e to the 3x plus c2 times x e to the 3x, plus y sub p. That's the solution to this equation. And it's a particular solution. It has no arbitrary constants in it. So that's the general solution in practice. Now, when we solve homogeneous differential equations, when we solve non-homogeneous differential equations, it's actually very simple. It just involves two parts. First, you're going to solve the corresponding homogeneous ODE, which I will call DE sub H for homogeneous. And that's going to allow you to find that y sub c. And then once you have y sub c, use a known method you're going to use a known method to find y sub p. And the methods will be discussed later in this unit. Then the general solution is just y equals y sub c plus y sub p. So this is what we do in practice. We solve the homogeneous equation first. Then we say, okay, how do I find the particular solution? We've got a couple of methods for that. We'll use one of those. And then we'll add the complementary solution or complementary function. That's the solution to the corresponding homogeneous ODE to the particular solution. And that's the general solution. Okay, that is it for our studies of preliminary theory of higher order differential equations. I'll see you in the next video.